Okay. We have two more problems in rates of change. You're going to get one of these two problems. A problem based on this problem, similar with maybe different numbers or different meanings, but it's going to have the same basic content, and one for this one. Okay, you get one of the two. Okay. You say if T equals 3, temperature is 40 degrees, T equals 12, temperature is 100 degrees. And we put that information on a graph. Well, letting little t be the time in minutes, we're going to put time in minutes here. Then we're going to put the temperature in degrees on this axis. Okay, because you're asked to find the rate of change of the temperature with respect to time. I'm using capital T for temperature, little t for time. The 2 points in the graph are pretty obvious. T equals 3, temperature is 40 degrees. Well, here's our line for T equals 3. Here's our line for T equals 40, wherever it is, here it is. And where they intersect, that's a point on the graph that represents this first line. Second line of information says T equals 12, temperature is 100 degrees. So we've got T equals 12 here. We've got 100 degrees up here. Okay. Now I can write T equals 100 and T equals 80. I don't have to write T equals 100 degrees, T equals 80 degrees on this graph because I said temperature T in degrees. You want to specify that. Okay. Time T in minutes. You put that down and you're going to be better focused and less likely to make mistakes. So I really recommend that you label your axes like this when you have meanings to your quantities. Since I said T is in degrees, I don't have to write degrees on my big T's. Okay. However, when I calculate the rate of change, I'm going to want to put the degrees in the minutes. All right. Well, we do triangle, the rise, and the run. The rise is easy to find. Go from 40 to 100. The rise is 100 minus 40, which is 60. You go from T equals 3 to T equals 12. The run is from 3 to 12, which is 9. 12 minus 3 is 9. So you find delta T is 60 degrees, delta temperature, delta big T is 60 degrees, delta little t is 9 minutes. You divide that, I think you get 6.44 degrees per minute. I don't want to see just 6.44. I want to see the degrees here and the minutes here. And I want to see the degrees here and the minutes here. They're divided here, just like they're divided here. It means degrees per minute. Okay. Number 110, it's the same type of thing. You're given some creature, maybe a Thanksgiving turkey. Now Thanksgiving turkey will grow faster than this. I don't know what it is, but whatever it is, it starts out at 26 degrees at some time, and 8 months later, 26 degrees, 26 pounds. 8 months later, it's 56 pounds. That's the information you're given. Here's how it looks on the graph. I'm using W for weight, okay, in pounds. And I'm using T for time, with time T in months, weight W in pounds. Okay, the rise is, oh, here's another mistake. The rise is from 26 up to 56. I would put the dotted lines in here, label like I did here. But I had to go kind of small in this graph, so there it is. And the rise is not delta T, the rise is delta W, because rise, well, the rise is vertical and the vertical coordinate is the weight. Okay. So, and look at what I did. I put delta W down here. Got them backwards because I wasn't thinking. I wasn't paying attention. So that's delta T, not delta W. There's our rise, there's our run. Average rate of change is delta W over delta T. And I did it right here. It is 30 pounds over 8 months. I call this one delta T, call this one delta W because I wrote it down without thinking, without paying attention. saying not like I do, pay attention. Okay, 30/8 is 3.75. You got the pounds and the months, and they give you this calculation, pounds and months. And when you divide these, you end up with pounds divided by months or pounds per month. Okay, so we're gonna have a problem like one of these. And then the last thing is composite functions. And let's see. I had to squeeze these in because I was completely out of board space. Actually, I wasn't, but I couldn't figure it out. Okay. This is like number 111, I think. H of x is -5 over the quantity -5x plus 5 squared. Make sure you understand that what I type, what's in typewriter notation on the sample test and on your test means this. Okay, just order of operations tells you -5 slash this quantity squared is -5 divided by this quantity squared. You have a fraction expression. Okay, now if this is f of g of x, then what could f of x and g of x be? In other words, this is a composite function. How do you break it down into an f of g of x? What I say to look at this is g of x is the first thing that happens to x. What's the first thing that happens? If you have an x value, you plug it in here, and then you do -5 times that plus 5. Okay, so it makes sense to let g of x equal -5x plus 5. If g of x is -5x plus 5, then what function of g of x is going to give you -5 over -5x plus 5? Well, that would be f of x equals -5 over x squared. And you should be able to easily verify that in this case, f of g of x is replacing x. So if we replace this x, you get -5 over the square of g of x. And of course, g of x is -5x plus 5, so you get -5 over quantity -5x plus 5 squared. So if you do your f of g of x honestly and rigorously, you'll see if this matches this. It doesn't, try something a little different. Now there is an alternative here, and it doesn't matter which alternative you would use. There are often multiple ways to write a given function as a composite. Alternatively, we could use g of x equals -5x plus 5 squared. We could have the thing squared already. That's a perfectly good function. And then f of x is -5 over x. Okay. Well, you can verify that that works. F of g of x. Well, you're placing x with g of x, so it's -5 over g of x. And g of x is -5x plus 5 quantity squared. And there we have our h of x function. Okay. Then there's another example. I want to do this slide. I think it's on this one. Yep. Okay. Note 112 composite function with h of x equals quantity 2x minus 5 squared plus 1 over quantity 2x minus 5. Okay. And you want that to equal f of g of x for some f of x and some g of x. Well, you start looking for g of x, and 2x minus 5 is a good candidate because it appears here and it appears here. Originally, when I wrote that, it was 2x plus 5. If it was 2x plus 5, you wouldn't even be able to do this. Okay? But since it's 2x minus 5 and it matches what we have here, we're going to let g of x be our 2x minus 5. Now, what happens to our 2x minus 5? It gets squared. And then to that, you add its reciprocal. So g of x, or f of x, would be the squaring function plus the reciprocal function. In that case, f of g of x is what? You're replacing x with g of x, both here and here. You place it here, you get g of x squared. Replace it here, you get 1 over g of x. And then, since g of x equals 2x minus 5, this gives you this, which matches this. And this gives you this, which matches this. There it is. Now that's tricky. You want to practice that, but you have problems of that nature. And I kind of modeled these after problems that I saw in the homework. So make sure you understand the homework. Okay? And also remember, I'm happy to answer questions. And if you want more examples and more sample problems, I can generate it by the millions. Okay? Once the thing is done, I just tell it how many I want. Now, millions might take an hour or two, and then I wouldn't be able to get the file too because it'd be too big. But if you want 10 sample tests, just make sure you understand what could appear on the test. That's fine. You're going to get one of these two. You're going to get a piecewise function. You're going to get an inverse function. You're going to get two rate of change functions. Okay? And you're going to have two of those construct the graph and verify everything functions. Again, the construct a graph and verify the functions. There are only two of those problems, but that's at least half your credit. So you want to master that. It's achievable. It's not that hard to do. You just got to practice until you get it right and until it kind of sinks in and you understand what's going on. Okay. And same for these other problems. They're predictable. It's achievable. It's very possible everybody can make an A in this test. You need 90%. And I hope everybody will. I hope everyone who makes 100. Yeah, somebody's going to make a mistake. All right. So good luck on that. And look at the longer videos if you didn't understand everything I said here. They're in the same order that these are. Okay. And it'll be clear once I get them posted. It'll take a little while. Okay, very good.